Good evening, I am Shripriya. I have recently finished my PhD in the area of corrosion. Today I will be handling the class with electrochemical testing using EIS. This is the brief outline of my presentation. First I will be going through the principles of electrochemistry, AC versus DC method, and then the actual testing, 2 electrode system versus 3 electrode system, the different EIS plots we get, Nyquist plot and Bode plot, validation of EIS data using different techniques, and then formulation of equivalent circuit modeling followed by case studies. Corrosion is an electrochemical process. So, it involves movement of ions and electrons. So, if there is a movement of electrons, we know that that is current. This current is called corrosion current, but this current cannot be directly measured as it is in the equilibrium state. So, to measure the corrosion current, we need to understand the principles of electrochemistry. What happens when a metal is immersed in a solution? So, when a metal is immersed in an electrolyte, there will be a reaction. Because of the reaction, there will be a surface charge formed on the metal. Due to this surface charge, ions from the electrolyte will move towards the surface and gets adherent to the surface. This adherent layer is fixed layer, and surrounding that layer we have another layer called diffuse layer, where there will be a dispersed ions and then there will be electrolyte. So, this is the typical representation of a double layer. First we have a surface layer with some ions on it, and then stern layer which is the adherent layer followed by a diffuse layer, and all the stern layer and the diffusion layer together forms the double layer, and then we have a normal electrolyte. So, the components can be represented as the metal which is this, and then electrical double layer which is represented by a capacitance and resistance in parallel, and then we have a solution resistance. So, this is represented by electrical double layer. This and this together forms the electrical double layer. Here you can see that the diffuse layer is not a fixed layer. So, this capacitance is not ideal in nature and can be represented as constant phase element. That means, it is not ideal in nature. Second, this part you have electron transfer resistance. There are 2 terms which are used interchangeably, that is charge transfer resistance and polarization resistance, but they have a subtle difference in their meaning. For now we will represent it as Rp alone, and then we have this resistance, that is the normal electrolyte solution resistance. So, now we know that we have a system with different components, but how to measure the current that is happening in this system? Since it is in equilibrium, we need to give a small disturbance by applying either current or voltage. If we are applying a small current and then measure the voltage that is happening, that is called galvanostatic. But if we are applying a small voltage and then measure the current, it is called potentiostatic. This potentiostatic is the widely used mode because it is applicable to lot of applications, and it is flexible also. There are different advanced options available, that is, you can apply voltage at specific frequencies in different systems like Solartron. Galvanostatic is usually employed for large power devices, that is fuel cells and batteries, where applying smaller voltage will be difficult for the system to fluctuate. So, instead of applying voltage and measure the current, we apply current and then measure the voltage. So, we now move on to the next thing based on potentiostatic mode. In potentiostatic mode, you can either apply AC voltage or DC voltage. If you are applying AC voltage, there is a, here you can see there is a charging and discharging that is happening. When charging happens, the electrode surface will have a charge and then the diffuse layer will be pulled towards it. When discharging happens, the diffuse layer move away from it. So, this response will yield some data we will understand about the system. For example, if it is a system has capacitance, if the system has resistance, the response from this kind of charging and discharging will yield us data and we can understand more about the system. Second is DC voltage. In DC voltage, we will apply a unidirectional current. We are charging the electrode. So, this will push the diffuse layer away from the electrode, and because of the constant pushing, there will be a small change in the surface. So, the electrode will get roughened. So, there is a small disturbance in the system as such, and this layer, that is the distance between the electrode surface and the double layer, it is not purely capacitive in nature. There will be a small current flowing, that is what is represented, and there will be a this is called capacitance leak. So, when we apply a AC voltage over a DC voltage, there are several advantages. The first advantage is there is a minimal disturbance to the system. Then with the help of DC voltage, we will earn only the resistance of the system. But when we apply a AC technique, we will be able to identify the individual components of the system. For example, the solution resistance, the double layer resistance, that is steel interface in our case, and then there is a passive film formation. In this electrode, if there is a thin film formation, whether it is porous in nature or fully adherent, that also we will able to know from this AC technique. Then we can also determine the reaction kinetics. For example, there is a reactive species that is adherent to this layer. So, how fast or how slow the reaction is happening, so that there is a change in this layer, that also can be determined with the help of this technique. Then we have inhibitor efficiency. So, if we are adding inhibitor to the concrete, we assume that there is a film formation that is happening at the steel cementitious interface. The formation of the film and the efficiency of the film can also be determined by periodic testing. Then we have coating. If we have used coated rebar, the efficiency of the coating can also be determined. All this will be discussed in detail later. Now, we move on to the actual testing. So, when we go to the lab, we will have a confusion whether to use a 2 electrode system or a 3 electrode system. So, when we use a 2 electrode system, what happens is there are 2 half cells here, one is here and one is here. So, when we connect the 2 half cells with the potentiometer, what we measure is the response of the whole system. So, if we are not if we do not want to differentiate between the reactions and we want to only the resistance between the systems, that reactions that is happening, then we can use the 2 electrode system. Otherwise, if the working electrode is too high of impedance, then in that case also you can use a 2 electrode system. This is the typical example of the 3 electrode system. Here you can see this is the working electrode. Working electrode is always the system under study. Then there is a counter electrode where we apply current or we measure the current from the potentiostat, and then we have a reference electrode. The reference electrode is a standard electrode where we know the potential of the electrode. So, we measure the working electrode potential with reference to this reference electrode, and then we apply a small potential and then observe the differences that happens in the response. Also, the whole system like counter electrode, working electrode and reference electrode, all the 3 together forms the corrosion cell. Once we connect the corrosion cell to a potentiostat and start the testing, we get 2 types of curves. One is called Nyquist curve, the second is called Bode plot. So, the Nyquist plot is real versus imaginary. The real component is the resistance that is in the system. The imaginary component, if it is here, then it is capacitance. You have to note that the Z double dash represents the negative imaginary component. Just for ease and our sake of understanding, we always mention the capacitance in the top and the inductance in the bottom. But if you see this carefully, you will understand that this curve does not tell anything about the frequency, at what frequency we yield this type of graph. So, for that we need to have this Bode plot. This plot is a function represented as a function of frequency. So, here you can see that the frequency starts from 10 to the power 5 to 10 to the power minus 2, and this phase angle represents the lead or lag by the current. So, if it is negative, then that means it is capacitive in nature, that is the system is lagging, and if it is positive here, then it means that it is leading the current. Then you have the Z modulus. Here in the Z modulus, if you see, this portion represents the solution resistance and this portion represents the solution resistance plus polarization resistance. But you can directly take these values only in case of metal aqueous system. For a system like steel cementitious interface, like what we do for steel corrosion in concrete, this is not straightforward. Simply you cannot take it like this. You have to formulate a equivalent circuit modeling for extracting the parameters. These are the different types of EIS graph you can get. If you get only one element, that is RC element, that means you have only one kind of double layer that is forming, and if you have different RC elements, that means your system is behaving differently. So, depending on the system only, you nature of EIS curve will differ. So, this is another typical example. Here you can see that it is coming in the negative region. So, if it is coming in the positive, that means it is a RC, that is resistance and capacitance in parallel. If it is coming here, that means RL, that is resistance and inductance in parallel. This means that there is some reactive species adherent to the electrode surface, and within the ions it is having a inductance nature. It does not mean that there is a inductor there. It means that the arrangement of ions near the surface of the electrode interact within each other and induce a inductive nature. Now, we will move on to the different types of artifacts which we get. Artifacts is nothing but distortion of EIS curve. Why this kind of distortion happens? The distortion can happen in two levels. One is due to the arrangement of the electrochemical cell, that is the arrangement of working electrode, counter electrode and reference electrode. If your arrangement is very complex, it will distort the distribution of current and cause distortion in the EIS curve. So, if you have a cell like this, this is the Lugin probe and then this is the working electrode. So, if I keep the Lugin probe very close to the working electrode, then there will be a current cutoff that happens between the working electrode and the tip of the Lugin probe. So, this may induce the distortion like the blue curve. So, if you do not want a distortion like this, what you should do is you should simply keep the Lugin probe slightly away from the working electrode. Then there are other kinds of artifacts that induce because of the impedance of the Lugin probe. So, if your Lugin probe is narrow, or if your Lugin probe has some bubbles, or if your Lugin probe has some crystallization that happened in the solution, all this will create a high impedance inside the tube. Because of this, there will be a non-uniform conduction and this will distort the curve in the high frequency region. You may note that all the distortion that happens are in the high frequency region. So, you can easily identify whether this is a distortion or not. This kind of distortion can be eliminated by simply adding a metallic tip at the bottom. So, one may argue that here by looking at this graph, you may need not include a Lugin probe to avoid this artifact, but there are some cases where the reference electrode, while keeping it in the electrolyte, may contaminate the electrode and cause instability of the reference electrode. We do not want that kind of instability, that is why we introduce the Lugin probe, and then when the Lugin probe has some issue, we can eliminate with the help of metallic tip. So, this is another interesting graph I got. One may look at this and think that this is a very good graph, it does not have any distortion in the high frequency region. For example, it is not, the 0 is here, so it is not in the negative side of the impedance. But this kind of graph I got it in a new system, so I thought it is a because of the species that got adherent to the surface. But when I looked into the literature, two arguments were there for this kind of graph. One was due to the instability of the potentiostat, and the next was due to the reactive species adherent to the electrode surface. So, to check whether it is an artifact or not, what I did is I went and checked in another machine potentiostat. When I checked there, I found out that my potentiostat was not working properly and started inducing these kind of artifact. So, the main important thing about this are you should understand whether the curve is artifact or not. How can you identify that artifact? That we will come later. So, you can have artifacts because of the chosen parameters that you use for testing. For example, if you use a amplitude which goes to the nonlinear region, that is working electrode will have some potential. We want to measure the current, so we apply small potential and disturb the specimen, and then we understand the current. But if the disturbance is too high, then it may go to a nonlinear region and it will not come back easily to the original state. So, when that kind of non-linearity happens, then we are not able to get the actual corrosion current. So, if you see here, the blue curve is 10 millivolt, which is a small perturbation, and in the red curve is 50 millivolt, which is a large perturbation. There is a shift between the blue curve to red curve. This indicates that the system has gone to the non-linearity region. If it is in the linear region, it will trace back the same curve as that of the 10 millivolt. So, you can understand that this is a distortion and we should eliminate this kind of high amplitude when we are using the testing. Next is frequency. When you have a very high frequency, the cables will attract the noise from outside and this may distort the curve in the high frequency region. So, to eliminate that, you have to use a low frequency, that is 10 to the power 5 instead of 10 to the power 6, or you can use a Faraday cage which can avoid this kind of noise pickup by the cables. So, there are three types of artifacts we have seen. One is due to the electrochemical cell arrangement, next is due to the instability of the potentiostat itself, and third is because of the chosen parameters. For steel in concrete, amplitude of plus or minus 10 millivolt from OCP and frequency of 100 kilohertz to 0.01 hertz can be used.